In this video, I'm going to go through the code that's in the text. I just want to point out a few things. And in particular, so I ran everything already, but some parts take a long time, so I just want to sort of explain some of that as we go through. So we read in the packages, read in the data set. In the data set, you can look and see the X variable that we want to predict is misstate. This is like a fraud variable or a financial misstatement variable. All of the other columns to the right of that are to predict misstatements. So this is current account, current assets, the total current asset amount. This is accounts payable, total assets, some others along here. Set seed makes it so that when you repeat any random things, it'll do the same thing, so it's not really random. Then we're going to set up the training data set and the testing data set by a random sample here of the main data, and then anything that's left goes into the testing data. We're checking here how common the misstatement variable is in the training and the testing data. Turns out they're both a little less than 1% and similar. When we initiate this here, we can use up to the number of threads or the number of cores in the machine. Mine has 16. You see that with this detect cores. If you use all of them, you can't do anything else while it's running. I use less than that. So usually I leave maybe 2 less. Here I'm using about half of what I have on my machine. Set up the training data, move it over into the Java environment. This is the piece here. So this is what's in the text. I've added this before it and these after that. That is there. It's a way to check how long this process lasts. So this piece of the code on my machine took 50 minutes. I don't want to sit around the whole time and watch and see how long it took, so I set this up to check how long it takes. The reason it takes 50 minutes is because I'm running maximum 25 models. It turns out to do around 25 models. And I'm also using the whole data frame. So notice here when I set up the training data, I'm using all of the columns. So this is here from ACT all the way to the last column over here. So you don't have to do that, right? You could do ACT, let's say to cost of goods sold. You could change this to here and just keep those, and it would run a lot faster. But if you want to do it just like in the book and wait a little while, expect to have this take some time. You can get the best models come out of here. This is the get leaderboard part. And it shows you all of the models. So it ended up running 27 models. That's because it stacks on some others at the end. It has deep learning, so those are neural network models. It has gradient boosted machines, some other models. These are tree-based models. We'll learn about each of those later. The best model is the top one, stacked ensemble. An ensemble model is combining a bunch of the models together. And this is the AUC is 81%. You'll see later that sounds pretty good. So 1 is max, 0 is min, and 0.5 is sort of a toss-up. Sounds sort of good, but it's mainly because it's predicting zeros instead of ones, which I'll show you in a minute. You can then get the best model. So we already know here it's the stacked ensemble, but if we do this one, we get more of it. So we can see here at the top, it's a stacked ensemble. We can see the AUC. We get the confusion matrix. And notice the confusion matrix says vertical are the actuals, across are the predicted. So that means up and down here are the actuals. Left to right here, 0, 1 are the predicted. So when it's actually 0, there were 96,000 that we predicted to be zeros. 993 that we predicted to be ones. So this gives us what percent of these we got wrong and for zeros. Then the ones that actually turned out to be ones, there are 640 of those. We predicted 125 to be ones, but we predicted 515 to be zeros, but they were actually ones. So this gets us how many were wrong as well. All right, so that's the confusion matrix. Notice that where most of our data is coming from are where it was actually a zero and we predicted it to be a zero. That's our 80, most of our 80% is we're getting that right because we're not doing too great in terms of predicting these ones, right? We like where it was, we're getting more of the predicting ones where it's not a one than the other way around. Okay. Then variable importance you can typically do, but an ensemble method, it doesn't generate variable importance as it's creating the method, so it won't work here. But you could do it if you had a different method. Okay, so then we move over the testing data. We can do predictions with that, the model we've created and the testing data, and we can save them. So notice we moved it back over to R. This as.data.frame moves it back over to R. We look over here, we see pred. This is a vector of factors, so ones and zeros. We can then use it for some other purpose, like we predict this particular company has a one, for example. But to use $x, which is going to do more explanation, we need to make it a number. So this is just taking what's in the testing data in H2O. The first column is the y variable. It's making it a number. This creates the explain object. So explain H2O with the model we created. These are the x variables. So everything but the first column, and then this is the first column, which is the y variable. These next pieces are what we use to explain and understand how the model worked. So model performance. Notice this is all on the testing data. This is not training data anymore. So on the testing data, it shows us that the AUC was 83 or 84%. So slightly better than on the training data. Normally, I would expect it to do worse on testing data, but most of this is just coming from getting zeros right anyway. This variable importance, so notice inside the functions are all this explain object. So variable importance can take a little while, and this PDP can take a little while. So if you look up here, let's see if I still have some of it. So it'll look like this. It's going to keep going, because it has to go through lots of instances of it. So let's look through quickly what this tells you. So we have this feature importance. At the top here, the top one is the most important, and this is how much AUC is increased by adding the variable to it. So here, adding the column soft assets has the largest impact on increasing AUC. Inventory also has a fairly large impact, and then it sort of goes down from there. Then the next one, the PDP, partial dependence plots, looks like a little bit of a mess. You got to open it up to see more. And if you have more columns, it's hard to read too. But this tells us something about, so let's look at soft assets because that says it's the most important. And this is a scaled variable. It goes from 0 to 1. And let's see what it says. So it says, the x-axis, so going from left to right, is increasing the variable. So going left to right means larger soft assets, and then the y-axis is how much the prediction changes. So as soft assets increase, the prediction is higher that there's a misstatement. So higher soft assets means higher probability of having a misstatement or fraud or at least in the model, that's the prediction. Whether that is actually the case or not, don't know. Inventory looks dramatic here, but it's not that important in the importance plots. But what we see here is going from 0 to a smaller, bigger number increases the probability of misstatements a lot. Going from near 0 to a 5% probability of misstatement, but then it goes down from there. Well, an important part here is this is most of the distribution is in the smaller tail of this. There are fewer observations as you get further out here. All right. And you would only know that by looking at the data. And so you could do that with any of these. These try and tell you, does something make sense? So in terms of soft assets, that kind of makes sense, right? Like soft assets would be things where someone has where a manager has flexibility in how they report, and that would seem to be times where you might get more misreporting. All right. And then once you have all of these, you've trained it, you shut down the H2O instance, so that shuts down the Java setup, which means you won't be able to access it anymore. So you may or may not want to do that. But once you're happy with it, you run this, close it off. Are you sure you want to shut it down? Yes, and then you're ready to move on.